So, good morning everyone. And welcome to the 2015 Summer Intern Presentations, number 1. And it's my pleasure to have, if you don't know me, my name is Hugo Leon, I work in design too, and I was given the great pleasure of mentoring 2 students from New York Poly, Sue and Siraj. And during the summertime, what they gave them to do was prepare spreadsheets for checking sheeting design, pavement design, and some estimating spreadsheets that will help us do some work internally. So before I go on, any questions you have, please write them down now. At the end of both presentations, you can ask some questions. Another thing is, the spreadsheets that we're going to be showing today will not be handed out to the public. We have to go through a little quality control. I went through the 2-strut presentation that she's going to do today, and I checked the calculations, they're okay. And I know somebody in Design 1 here, I don't know who it is, got their hands on that. So don't spread them out yet until we do a little quality control on them. When we think they're ready to put out for the whole population of the Design 1 and 2, then we'll do that. But until then, don't know that it's out there. It's going to help you guys out in the future. And it's all because of these 2 great students from NYU Poly. So without any further delay, let's Siraj is going to give some statements.
Good morning, everyone. My name is Raj Kumar, and I'm the one summer intern for Design 2 for infrastructure. Some information about me is that I go to NYU Poly, and I'm studying civil engineering and construction management. And this summer I created some cost estimating templates for highway construction templates. So here's the agenda. I created 5 templates this summer. They include a general template, a highway perimeter template, a pavement area template, a pavement marking template, and a pavement design spreadsheet.
Can you speak up, please, a little bit?
Oh, sorry. Got it. First, I created a general template. Here we have the description and the units. This is what the spreadsheet will output. The input are the item numbers and the unit. The item numbers and the location. So using the, I think so, yeah. Yeah. That one? Yep. So here we input the item number based on the DOT specifications. You give in the item number, suppose 4.09 AM, and you get the description, the steel phase concrete curve, and along with the units. And then you would input the location you want. Suppose you want on J Street between Metal Avenue and Flatbush Avenue, and then all you have to do is just input how much of that item you want. And then in the end, everything is totaled up and output for each individual segment. Next, I have a summary chart for the same spreadsheet. The output in this file is, again, the item description and the units. However, we have to input the item number and the quantity and the unit price once again. So suppose we have to estimate how much total steel phase concrete curve we need for a specific project. We would input the quantity and the unit price to get the exact price. Here we have a layout of how I would do the highway perimeter template. We have, suppose, like 4 sidewalks, and then we're going to calculate the total perimeter of the sidewalks using this calculator. We're going to calculate the perimeter using the curve radius, the angle of the curve, and 2 different segments. In addition to that, we'll have the length of the driveways, which will probably require some extra reinforcement. And if you use the next slide, I broke down the different segments based on the inputs that I described before. And all of this information is inside of the templates themselves. Next, I created a template to find the area of the roadway pavement. And in this pavement design, in this area of the pavement, this is item 4.02. Here we have various inputs, which include the radius, the angle of the curve, and the length and the width of the actual roadway. First, we're going to calculate the area just outside of the curve, which everything will make more sense using the next slide. And we're also going to need the length and the width of the roadway. Go to the next slide. So here we can see how we're going to find the area just outside of the curve, which is going to be one small portion, and then the rest of the portion is going to be the length up to the beginning of the curve and the width of the roadway. And that's going to calculate the area of the entire pavement. Here we have how I got the math behind getting this equation. It's some geometry. I created a circle and a tangent line. And I realized that if I incorporated the radius of the circle into this diagram, I was able to find the area just outside of the circle, which is exactly where I needed. My fourth template was the pavement markings template. Here I'm converting the pavement marking we use into linear feet. We're going to input the street segments, suppose J Street between Myrtle Avenue and Flatbush Avenue, and we're going to also input the type of marking we need. Suppose we need a regular crosswalk line. We can use a drop-down menu and select which exact marking that we need. And then using the length of the total crosswalk line, we're going to input that underneath the length. Suppose we need 5 feet of crosswalk line, and that's going to be converted to linear feet. Next, we can use that same information and it will be organized into 2 different templates. The first one is simpler, it's very familiar because it's from the general template. The different pavement markings can be summed up and categorized between the different street locations. Or the different pavement markings can be categorized based on the markings themselves, and we can find the total amount of markings we need. So for like, suppose we have various bike lane arrows, we're going to sum up using the previous template how much bike lane arrow then we need. Lastly, I created a pavement design spreadsheet using the DGC guidelines. We have to input some basic parameters, which include the soil characteristics, the annual daily traffic, the percentage of trucks, and whether or not it's one or two-way traffic. And that is going to provide us with the equivalent axial loads for both concrete pavement and flexible pavement. And afterwards, we get the design of the concrete pavement. And then we're going to check this number using the normal graph provided in the DGC guideline. And we're going to input that under D via figure 4. And if that number doesn't turn out to be the same number as the initial depth, we're going to try another value under D new. And this D new is going to calculate a new equivalent axial load, which we're going to check once again. And then if that number is fine, then we're good to go. And then our final design will be provided for both Class A and Class B concrete. Using the same values from the previous spreadsheet, we're going to incorporate that into the composite pavement. The depth is going to be converted into a different height. As you can see right here, which H rounded would be 7.5 inches for composite pavement. And there's going to be 3 inches of asphalt concrete for the design of the concrete pavement. Finally, we have the design of the flexible pavement using the same parameters from the first sheet. So you can see everything is already input and from the first sheet. And then we're going to have to check our structural number for the flexible pavement spreadsheet. And we're going to decide on which surface material, which subbase material, which base material we're going to need. And we're going to have to put in the depths of each of these materials to get the final design. As you can see, like one general trend is that the inputs are in orange output, in orange boxes, and then the outputs are usually summarized or in a gray box. Something I've learned from this process was that a lot of the databases are much more effective if we create them using index and find rather than VLOOKUP, because a lot of the information gets really like mixed up here and there. So like doing a simple like Google search to find out how to reference information using index and find is really helpful. And if there's any questions while you're reading the spreadsheet, you can just use the instructions provided in the demo. Yep. And that's all. Thank you very much.
Now we have Sue for the awaiting spreadsheets for sheeting. This computer is slow.
Good morning, everyone. My name is Intern, and I'm currently a ESMS student in civil engineering from NYU Poly. And today, what I have to present to you are sheet pile design and calculations. And I'll go over exactly what I've done for the summer, and I'll go through, So, in my presentation, I'm going to give a brief introduction of my project over summer. Next, I'll do a design overview of a two-stroke non-watertight sheet pile design, a simple design procedure so everyone can design their own loading for the loading diagram, and finally, a sample calculation tutorial with my spreadsheet. So over the summer, Hugo asked me to make different types of Excel spreadsheets so everyone here can check the design of the engineer's calculations. So what I did was for both watertight and non-watertight sheeting, I did the 2-strokes, 3-strokes, and anchor rod designs. And since the 2-stroke non-watertight is the most typical design, that's what I'll be talking to you about today. So when you first open up my Excel sheet, the first tab you'll see is called Documentation and Instructions. And it gives you the instruction on how to use a spreadsheet, as well as explanation of the calculations I've done, design standards and references I used, and it also tells you where exactly I located them, so you don't have to go through a bunch of different manuals to find it. And finally, the shear moment equations that I derived to use those calculations, use those numbers for my calculations. Next tab is the biggest one, 2-stroke sheet piles, and this is where you'll do your calculations. You'll also input the numbers that the engineer gives you, and my Excel will automatically calculate the loading diagram and check design of the engineer. And we'll go to that in my sample tutorial. Next is called Quick Input and Summary. So once you're accustomed to inputting the numbers in that calculations tab, if you don't want to go through scrolling down through all the calculations, what you can do is, in this tab, just input whatever numbers the engineer gives you in these blue boxes. You click on the button and it automatically calculates everything for you in a simple, quick summary. So it's really convenient once you understand the Excel. Last but not least is shear moment diagrams, and this tab calculates the maximum shear and maximum moment that you're going to use in our design. And once you input all the numbers in the calculations tab, it does it for you automatically. So I'm going to go over the design procedure that I use to calculate the loading for the load diagram and how to find T1, T2, and RB, which are the strut forces. So first, we're going to assume that in this loading diagram, it will act like a simple beam. And wherever these struts are located, T1 and T2, we're going to assume that it's a hinge. Because if you try to find T1 and T2 by taking the moment from RB down there, we're going to have two unknowns with one equation, and you know we can't solve that. So first, to solve for T1, we're going to calculate the areas of sections 1, 2, and 3, which is pretty simple because those pressures we see are already calculated for us by the engineer, so it's A, B, and C. So all we need to do is find the area of the rectangle and the triangles. Next, we're going to take the moment around T2 to solve for T1, and that's basically just the loads times the center of each shape, and you can see that from our calculations up here. T2 is the same exact concept and idea. We're just going to find the areas for 4 and 5, and then you're going to take the moment around RB to solve for T2. It's the same exact process as T1. And then finally, for RB, from statics, we know that the sum of all the forces in the y direction equals 0. We're going to take all the summations of the forces in the loading diagram, subtract it from T1 and T2, and then finally we get RB. So in case you want to do this yourself or do some simple hand counts, you can do that on the fly. And now we're going to do a sample tutorial of my Excel sheet. All the slides beyond this is basically for your own reference, but I think it's just easier for me to go through my Excel. It's literally just showing you where exactly I input my calculations, what to check out for, and such as this. So I think I'll just open up my Excel and show you how to do it. Oh. Anyways. So, like I said before, this is the documentation and instructions. When I load, let me see if they're not on. So basically, whatever you need to know about each tab in printing, you can also have jump down to whatever section you want in the documentation, just for some quick capability. So this is the biggest one that I'll show you. So let me go to the first couple of buttons. The first one is called Show Equations. So if you want to see what equations I've used exactly, you can just click on that button, and any of these equations will pop up to see what I've used exactly. You can hide them by clicking it again. Print spreadsheets. Basically, if you want a quick and easy way to print whatever tab you want, you just click it and press print. And then finally, clear input values. It will clear whatever is in the blue colored cells, because that's what you input. So for the sake of this Excel, I'll do that. So now you have a clean slate, and let me try to see what I missed. Is that everyone read this? Like gibbons and stuff like that? Okay. And let me do this one here. So you can see, like, just basically whatever the engineer would give you, like angle of internal friction is 30, I would just input that. This is 30. 30. And then all you do in the calculation is follow what he gives you. So then 20. And you can see the numbers will automatically calculate for you as you keep going up. So then this W and then 65. And then height. Let's see this. So these are all the bending stresses that we're going to use for our design that they gave us. And then next are the heights of our loading diagram, which is just here. So it's 14. A is 2. And as you can see, everything here is now calculated. It automatically calculates your load diagram for you, so just quick, easy, and simple. And then next, you can just put in whatever you need that the engineer gives you for their design. And the cool part is that in this diagram right next to it, it'll automatically change based on the numbers you give it, so that when you're checking your drawings compared to this diagram, you can automatically see if your numbers match with the engineers. So let's see that right now. Okay, so this is 10. 12. 3. And as you can see, now you say the design is okay, because based on the specifications, so DEP, it works out. And then you just keep doing that, just keep adding your numbers, and then you'll be done in no time. So this is 10. 10. And now you can see that everything works. You can check your diagram, and all the numbers that you inputted are now in this diagram as well. So this is quick, easy, and simple. And so once, scrolling down here is kind of a pain, so what I did was let's do inputs and quick input summary. You can just input everything you need, and you can see in the quick summary it's all kind of messed up because we don't have values. You set your values, and everything is already here. Everything is back where you were, so you don't have to scroll down and check for these. That's pretty much it.
So I'd like to take one little 20 minutes, but any questions for Sue or Suraj?
So what's the reason for the trapezoidal shape on this?
What's the reason for the trapezoidal shape for the loading diagram? That's why is it trapezoid? I mean,
that's the way the thing varies, the pressure varies.
Not usually triangular,
What was that?
not triangular, but chapter.
Well, no, because you have the constant, that one is the search of it that we're talking about, right? That's the search which is constant. The other one is varying based on the height of the soil. Okay?
Thank you.
But the normally the pressure comes with the triangular.
What was that?
Triangular.
The water also restricted.
There's no water on this
Yeah,
side.
this one is non-water
And
type,
water
which means there's no water. But for water type, there is a triangular load. So what you do is you have this trapezoid plus a triangular load to have. It's like a mixture. It's like a different shape, but it does take into account that triangular water pressure. But it's not. This is like a different design.
So like I said, the spreadsheets are not gonna be, we're gonna have to go through them ourselves. Get maybe a couple more professional engineers to look at them.
I have one question. Why the resultant force comes in the water? Why not
Which one?
the resultant force?
RV.
RB, you mean, why is it there?
Why is the water? Why
That's-
not the center? Is
Well, you excavate, all this area is excavated, right? All this area is excavated, so you have, the soil is down here. All this is down here. This is tending to bend this way, right? That's where you have the struts pushing against that. So you have a reaction down on the soil level, the bottom of the excavation. Right? That's where you have a
but
reaction.
the maximum load comes in the center of the center position in the water. But the resultant force, this is the resultant force comes in.
That's the resultant force of all this, it's for the whole diagram, but don't forget that these things are not, if this was a cantilever, you would have a maximum reaction down here, okay? But this is the design with struts that would distribute the load between the whole height of the actual excavation. You're right, if this was a cantilever, you have the maximum reaction down here, okay?
Shows calculation for penetration also.
There's an embedment, I think that's,
Embedment, yeah.
there's a minimum 2 foot, I think, according to the,
Yeah.
well, there's a calculation for the
Yeah, it's like
embedment.
minimum 3.5.
Minimum is 3 feet, but normally the embedment is calculated for when you have a freestanding, sheeting. That's when you have to actually design for the embedment. When you have a raised excavation, then you usually go for a minimum of 3 feet. Because most of the actual source is contained by the struts and the sheeting, so you don't need that much of a embedment.
It's a specs requirement, I believe. I don't remember.
Yeah, it's 3 feet, I think it's 3 feet, or 2 to 3 feet, I think it varies.
2 feet.
So,
2 feet, yeah.
So, like I said, the spreadsheets and the other ones are the same, similar design. They're one with water. And then I asked her just in case, normally we have the maximum I've seen is 16 feet in depth in excavation, between 14 and 16 feet. Anything beyond that, you're gonna start going into 3 struts, which we never really see many times. In that case, we do have the spreadsheets for that, but we haven't checked, I haven't checked it yet. Unless somebody else wants to check it, but without giving it away. No, actually, we'll check it, we'll get some other guys to check it that have a P license. And, when they're ready, we'll make them available to you guys. With the direction of the, assistant commissioner and Z and Dino, I guess, to get their approval from them. Hopefully this will give you guys a little easier time checking sheet designs submitted by contractors.
Very good.
Very nice, I like that. Especially for me or somebody else, you don't have to get the same calculations over and over again. So, but once you get the blessing of, the only thing is you gotta learn to put the right input, because remember, garbage in, garbage out, right? So you gotta know what you're putting in.
I think it will stop you if you have something that's really weird.
Unless I tell her to put a special program, if you put the wrong key, I'll give you a sap. So you probably do that, right, Sue? She's fantastic. Both they did a fantastic job for me. I like to really thank them a lot for their work. I mean, they really did that. come back and work with us, but we were trying. So, well, if anything else, we'll give you, I'll send you a copy of the PowerPoint presentations for your use.